Here again, we start our final lecture for the event with Adolf Wu. We start the final talk of the event with Mike Shapiro from Michigan State University. Thank you.
Thank you. Thank you for the invitation. I'm really happy to be here. And I would say that, as David mentioned in last talk, so I didn't meet Carlos until last year. But I was influenced by paper by Percy, Luen Chao, and Carlos, like this Dave Nanda, Lee Tomei paper from '86, like more than 30 years ago, right? It really changed my mathematical trajectory because I was introduced by this paper to the world of integrable system, and we did a lot of work after that. So I kind of, for me, it's like meeting antique heroes alive. So, when I met Percy first, and then these two guys, they're like alive and last year and full of life, and so enjoying not only mathematics but everything else. So it was like miracle. So I'm really very happy to be here. And in Russian tradition, there is always kind of customary to give alcohol to this conferences. So I decided to break this tradition. And this summer I was in Italy, and there is some small village of Castiglione del Lago, which do some special stuff. They do picture of different professions. So I went there, I thought about present for you, and I choose something which sound to me like most mathematically kind of connected, which is called geometry. So this is this picture. I want to give you this present. And then I learned that all that was really a mistake, because geometry translated from Italian means surveyor. I didn't know that, so I sort of apologize. But for me, it's kind of passing. Yeah. Anyway, so let me start with the talk. So in this talk also about some sort of integrable system, which is not exactly close to total lattice, but it kind of in the kind of ongoing work, it becomes closer and closer. So, like Percy said, everything is total lattice. So this is a report about kind of ongoing work with many other people. So, and many people contributed. This is a list. I don't want to go through all of them. Really, the subject was introduced by Rick Schwartz about '95, and it is very simple. So you just take n-gon in the plane, and you do the following operation. You draw all short diagonals. And inside this, like, you start with this pentagon, you draw all short diagonals, and inside you see another smaller pentagon. So you can define a map from the bigger pentagon to the small one. So if you start with hexagon, so, well, you will get this another smaller pentagon, you will see this kind of Star of David type shape, and then a map is from bigger hexagon to the smaller one. And now we can generalize this a little bit. So, and instead of we see that this construction is projective equivariant. So if you do projective transformation with original pentagon, you will apply the same projective transformation to the image. So we consider this section on projective classes. This is the first generalization. And second thing is that instead of closed n-gons, we can consider something which we call twisted n-gons when you have like infinite sequence of points with condition that there is one projective transformation M, which we called monodromy, such that Pi plus n is equal to M applied to Pi. So we'll have monodromy operator associated with this infinite sequence. And we consider the space of all such twisted n-gons. It's kind of easy to estimate the dimension of this thing because the space, you can think about this space as collection of n points plus monodromy operator. So collection of m points, each point in plane give you dimension, well, is described by two parameters. So you have 2n parameters for the number of points. Then you have to take quotient by diagonal projective transformation, so which subtracts the dimension of PGL3, which is 8. And then you add 8 again by describing this monodromy operator. So total dimension is 2n, and it's what's written here. So kind of you have this 2n dimensional space, and on this 2n dimensional space you define your pentagram map, and then you consider discrete dynamical system just iterating this pentagram map. And question is, what can you say about this discrete dynamics? So, for example, are there any conserved quantities? So how you can do computer experiments, which kind of there is a program written by Rick Schwartz, and you see that the motion looks really like quasi-periodic. So you start to suspect that there are some conserved quantities, and then you try to find them. So, and if you want to analyze this thing, that the best way is try to write some algebra. And not geometry, but some algebra. So kind of it's better to try some projective invariant coordinates describing this space. One way to do it is introduce, well, with each vertex connect two parameters. Vertex vi, you connect two parameters xi and yi. So in the following way. So if you have like 5 vertices with vi minus 2, vi minus 1, vi plus 1, vi plus 2, then you can draw such line through this containing the interval vi minus 2, vi minus 1, and then project this interval onto intersection with the line, and then project this one. You have like 4 points. 4 points on one line give you one cross ratio, which is projective invariant number. So this is your quantity xi. And then you can do it the same with this line, so you will get yi. In terms of this xi and yi's, your pentagram map looks like that. So it's just some rational map, and the question is to study invariance of this map. Well, the simple things to notice. So first, there is like hidden scaling symmetry, that if you multiply all x's by t and divide all y's by the same t, then you will see that what happens in this, for example, in this formula. Here t and 1 over t cancel out in numerator and denominator, and then 1t survives in xi. So xi star is also multiplied by the same t. So what I'm saying that you really have this scaling symmetry which doesn't act. And also easy invariance. So if you take product of all xi's, then these factors in numerator cancel with denominators, and factors, well, everything will cancel out. So product of xi's stays invariant. And the same for product of i's. And then not so trivial invariants, which are called monodromy invariants, are the following, that if you take such expression where m is your monodromy operator. Now monodromy operator is expressed also in terms of xi's, yi's. So you can think about the left-hand side as some expression in xi, yi's. This strange expression with rational exponents appears to be polynomial in xi, yi's. And you can decompose it into homogeneous components. each homogeneous component is invariant of this action. It is theorem by Ovsienko, Schwarz, and Tabachnikov. And you can do similar thing, replacing role of O n and E n, and replacing m by m inverse. You will get another collection of monodromy invariants, which we'll call E chi. So now the whole thing can be kind of combined in the following theorems: that pentagram map is completely integrable on the space of twisted n-gons in the following sense. So monodromy invariants are independent integrals. There is kind of right quantity of them, and there is also invariant Poisson structure of rank 2 if n is odd, rank 4 is if n even, and it is explicit expression for this situation. So kind of case in a sense case is closed. But then we can ask question: what happens if we take not the shortest diagonals, but say the diagonals of longer length? So, and we do the same procedure. Well, not hint, but kind of more or less the result of my talk is that this is also give you a completely integrable system in the same sense. And you can prove it by finding some connection with another subject which is called cluster algebra, which I'm doing for a long time. And this is what I want kind of really explain. Well, the next observation is by a student of Sergei Fomin, Max Glick, which says that, well, we can try to change coordinates, describing our twisted n-gons. Well, namely, this is one way to do that, but let me probably explain more geometric way to look at the coordinates. Now, instead of this left and right xi and yi for each vertex, so we can do the following. So let's take the side, which is labeled by I, and then do such projection. Like take 5 sides, consecutive sides. So we'll get 4 points on this line. We take cross ratio and we call it pi. And then also with each vertex we can connect like the pencil of 4 lines intersecting at this. So we can take cross ratio and call it qi. These pi's and qi's are connected to the old coordinates in the following simple way. And in particular, you see that pi's and qi's are not independent anymore. Because if you take the product of pi's times qi's over all I, then numerator will cancel denominator and the product is equal to 1. So pi's and qi's are not independent, but they satisfy one relation. And really, what they parameterize the quotient of the space of twisted n-gon by the scaling symmetry that we mentioned before. You have like one-dimensional fiber, so you do kind of consider projection by this scaling symmetry, and this is what parameterized by pi's, qi's. Well, okay, in pi's and qi's, the dynamic is you can write the formulas in terms of pi's and qi's, and dynamic looks like something like that, this formula, which really hinted connection to cluster algebra. And now let me probably give some brief explanation what is this cluster construction. You start with an oriented graph, which you call quiver, and then at each vertex of this quiver you assign some numbers, like some p1 and q1, and then p2, q2, something like that. And well, when you start with such picture, then you allow to do, you choose one vertex and you allow to do modifications. These modifications are called mutations. So you change quiver and you change also expressions written at the vertices. First, let's discuss what you do with the quiver, with oriented graph. So if you do mutation at this vertex, the result is like that. So you just, like for each pair of incoming arrow and outgoing arrow, you add one arrow from J to K. And then if you create arrows going into opposite direction, you just cancel them. And then you change orientation of all arrows incident to I. So if you do all that, so you have to add one arrow from J to K, and then you just change orientation of these guys, and the result is shown here. So we describe what happens with quiver. Well, this is example. For example, like if we start from this quiver and we do mutations, so what should we do? So we have incoming edge from 1 to 2 and outgoing edge from 2 to 5. So we have to add edge 1 to 5, which is added here. We also have incoming edge from 3 to 2, outgoing edge from 2 to 5. We have to add this edge. And finally, we have to change orientation of all edges incident to 2. So we change orientation, that one to the opposite. So one can check that kind of, this is mutation at vertex 2, this is mutation of vertex 4 here, and so on. Now formulas of Glick comes from such quiver. So if we just write P1, P2, P3 like on all circles, on all vertices in the inner circle, and Q1, Q2, Q3 here, and all circles in, well, written here, then what you can do mutations and all circles here. This will, the quiver will be almost invariant, except that all orientation of vertices will change. All orientation of arrows will change to the opposite, and then you just replace vertices of inner circle and the outer circle. So combination of two things results in in the same formulas for mutations, that formula for Pi and Qis. And in that sense, you notice that kind of all mutations, kind of formula of pentagram map written in coordinates Pi, Qi exactly coincide with a special sequence of mutations considered in cluster algebra for special quiver. Moreover, so if you consider different diagonals, longer diagonals, it also fits in similar quivers described like that. You take such part and then you just kind of take many copies of such thing and then kind of create quiver of many copies of different situations. Where okay, upshot is that kind of pentagram map written in coordinates Pi and Qi exactly coincide with the following sequence of mutations associated with the corresponding quiver. Now, from general theory of cluster algebra, we know that there exists invariant Poisson bracket given by the following formula. So if you have quiver, you just write the following, that Poisson brackets between, you have quiver where with some coordinates written here, like x1, x2, x3, and so on. So Poisson bracket between xi, xj is equal to number of arrows from I to j minus number of arrows from j to I times product xi xj. And this form stays invariant under mutations. It just comes for free from general theory of cluster algebras. So now notice that we already discussed that if we do this sequence of mutation which create pentagram which is associated to pentagram map, that the quiver stays invariant. So these coefficients are invariant under this sequence of mutation. And we get invariant form which is associated to pentagram map for free, just from general cluster algebra stuff. Well, now we want to discuss what about conserved quantities. Can we restore conserved quantities from to do that, and well, remember that Pi and Qi describe the quotient of our original space by scaling action. So we don't want this quotient. We want kind of describe our original space. So we want some dynamics in original coordinates, and we are doing that kind of using weighted directed networks and cylinder and the torus, which kind of is which was described in original paper by Alex Posnikov and also in our joint book with Michael Gehman and Alec Weinstein. So picture is like that. So consider such a graph, and well, such a picture written that, and we associate all edges with weights. Weights are either written on the edge, like here the weight of this h is x, the weight of this h is y. If nothing is written, it means that h is equal to 1. And plus we have some additional cut, which is drawn by blue line here. If h intersects the cut in the right direction, the corresponding h weight is equal to lambda, and if kind of it intersects in the opposite direction, the weight is lambda inverse. So introducing the cat is something like introducing spectral parameter in our picture. Well, if we have such a picture, now we can consider something which is called boundary measurement map. Namely, if you choose one source and one sink, one source on the left and one sink, we can take the sum over all paths connecting this left source with the right sink, product of weights of all edges in the path. For example, if you take 1, 2, so we have to take 1 here, 2 here, you can see in the picture there is only one path going from 1 to 2, which looks like that. Right? Now let's take the product of weights along this path. So this is weight 1, this is weight x, 1 and 1. So the total weight of this path is x, so which means that our boundary measurement B12 is equal to x. So all that together give us the following matrix. Well, you can check, for example, that element 2, 1, it is just this path, and this path cross our cut, so it gives us weight lambda, which is exactly stays here. Well, now if we have, now we will construct like bigger picture out of these elementary pieces. So the bigger picture is just obtained by concatenation of such elementary pieces, and concatenation of these pieces correspond to the taking the product of the corresponding boundary matrices. Why it's useful? Because on this picture we can introduce Poisson bracket between parameters of edges, which is done in some special way. Observation that this Poisson bracket between these parameters can be pushed forward to the corresponding boundary matrices. And in our case, they will induce the very well-known Poisson bracket on the space of n by n matrices, namely the standard trigonometric R matrix Poisson bracket. Well, then with this weight we can do the following, we can ask the following question. So with these networks, so can we do some elementary transformation of matrix which change the weights of edges but doesn't change boundary measurements? First thing that we can notice that there is gauge transformation. So if you take some vertex, we can multiply all weights of incoming by some parameter t and divide all outgoing by the same parameter t. The weight of the path won't change because the product will stay the same. The product of weights of edges of any path passing through this vertex will stay the same. And so this gauge group gives us kind of continuous family of parameters. Then there is also some elementary transformation which do not change boundary matrices, and there is finite number of them. Most important for us is the following one, so like which is called square move. Well, I probably don't have much time to discuss details of that, but just believe me that there is one non-trivial transformation which kind of doesn't change boundary measurement. This transformation looks very simple if we pass to gauge invariant parameters here. Now, what is gauge invariant parameters? So note that our network split, well, our quiver split the plane into such connected pieces which are called faces, and assume that we have like such situation. We have like piece. So with each face we can associate one parameter f, which is basically just the product of all weights of edges along the boundary. So in this case, when we well, there is natural orientation. So, and we take, we multiply by the h of the weight if orientation of h coincides with orientation of boundary, and divide by the weight if it's opposite. For example, here the face weight is product ABC divided by D, because orientation of D contradicts the orientation of the boundary. Easy check shows that this expression is gauge invariant. This is a standard way of obtaining gauge invariant parameters, and they don't change the boundary. Well, since we know that gauge operation doesn't change the boundary measurements, everything can be written in terms of these gauge invariant parameters. Well, this transformation has extremely simple form in terms of gauge invariant parameters. Namely, if you have something like A, B, C, D, E, then in terms of gauge equivalence, what happens, kind of orientation of this vertical arrows will change to the opposite one. And here it's written 1 over E. C is multiplied by 1 plus E. B is multiplied by E divided by 1 plus E. D is multiplied by E divided by 1 plus E. And A is multiplied by 1 plus E. Well, these formulas really remind us what happens in cluster algebras. So we can associate with the picture here the corresponding cluster algebra and consider the following. Like now let's take concatenation of our elementary pieces in such bigger one. Remember that well, this picture describes us twisted and gone. Because these parameters, x1, y1, x2, y2, x3, y3, and so on, can be thought as parameters of n-gon. Now we have pentagram map which transform this thing. What I want to do is I want to obtain this pentagram map as sequence of some mutation, of some elementary moves of this network. So first I do mutation and all this. You will see that here we have like five squares, and you should think about this picture drawn on the cylinder, which kind of is horizontally drawn. So let's do square moves in all these 5 squares here first. And after we do that, we will get similar picture, but this edge will orient it downward, this edge will orient it upwards, and so on. So after that, we can do some kind of shift of arrows which doesn't change boundary measurements because of other elementary transformations. For example, if you have such situation, then it's equivalent to kind of changing the changing the order of these things comes for free, so it doesn't change boundary measurements. So we can do these shifts, and using the shift we can restore the original picture, but parameters written on the edges will be different. And also we have to use gauge group to kind of kill kill some parameters and change the different one to restore parameters in the right places, non-identity parameters in the right places. So after we do that, well, here is kind of, let me show you quickly what happens here. So this is the original picture drawn on the cylinder. The first step, we will change orientation of all these edges, and then we do shifting. So we kind of move that, move that, move that, move that, move that. Kind of, we also can kind of have to do something like take one arrow from this side and attach it from the other side. So the result is kind of picture which look like original one. But after doing that, parameters, the corresponding parameters will change. Lemma says that the parameter change are given by these formulas, and they are really conjugated to pentagram map by the following change of variables. Well, again, corollary of all that we can sort of model pentagram map by considering the corresponding networks on the cylinder and doing these elementary operations. Now, how it's useful to see conserved quantities. Recall that our elementary operations consist of square moves and some kind of commutation relations. We already discussed that square moves doesn't change boundary measurements. So after square moves, all elements of boundary measurements do not change. What can screw them up is kind of when we take arrows from one side and other from the different side. This is equivalent to conjugating Q boundary measurement by some other metrics. But under conjugation, like specter of the matrix doesn't change, right? So the result is that if you consider now our matrix is, well, our metrics depend on spectral parameter lambda, and then we know that specter of this matrix doesn't change. So, like if you take characteristic polynomial, then coefficients of characteristic, we will get kind of polynomial in 2 variables, lambda and z. And these coefficients do not change under under the whole group of operations. So we get a large collection of conserved quantities, just from kind of more or less just from this connection with the cluster algebras. Then we have to show that this collection is an involution, but it's more or less automatic because, as we discussed, so our Poisson bracket that is invariant is pushed forward to the R matrix bracket, and for R matrix it's sort of kind of classical fact that coefficients of spectral curve kind of are in involution. So proof done. And the similar proof works for any kind of longer diagonals. You just change kind of our quiver a little bit. So you should change. Well, this picture would be changed a little bit, but kind of idea is more or less the same. Okay, this is the first part of the talk. Now let's discuss some generalization of this stuff. Marie Beffe and her student Philippe considered some generalization of this pentagram map to higher dimension. Like we consider the n-gon, but points of the n-gon we now interpret as k-dimensional subspaces of free k-dimensional space, like points of the Grassmannian k, free k. Okay, now if we have, so each point means a corresponding k-dimensional subspace. If we have diagonal connecting two points, then diagonal should be interpreted as sort of subspace generated by this, by n points. So diagonal is like 2k dimensional subspace. And if you have pair of 2k dimensional subspace in 3k dimensional space, then intersection in general position is k dimensional. So intersection point you have to understand as some mu points of the Grassmannian. So then you get a map from like bigger polygon to smaller polygon, but each point is now interpreted as sort of polygon in Grassmannian. So this is definition of Grassmann pentagram map. And the result of Marie Beffe and Philippe says that the Grassmann pentagram map is completely integrable. Now, when we have discrete dynamics, first of all, what does it mean completely integrable? Like, well, this question was discussed, and in a way there are many definitions of complete integrability. What they really meant here is that they can found a large collection of the right size of integrals that are preserved under this operation, under the evolution. But they didn't know, for example, even what if there is any Poisson bracket invariant under the action. So it's not like Liouville integrability. On the other hand, according to Kontsevich, what is the correct definition of integrability of discrete system? You just program it, like put it in the software, and let it run for 5 minutes. If it doesn't break, if it doesn't blow up, then it's integrable. If not, if you get like exponentially large numbers, if it's break after 15 seconds, then it's not integrable. So, which makes some sense. So it means that if your computer can run the numbers for a long time, it means that there is a lot of cancellations going on. So kind of algebraic entropy doesn't grow exponentially. So this thing is definitely satisfies kind of the definition of Kontsevich. Well, definition. Well, the result was sort of kind of Isosimov introduced some invariant Poisson structure in this case. Additionally, looking kind of borrowing from some kind of discrete difference operators. And what I have a kind of very good Michigan student, Nick Ovenhouse, and I asked him, so can we do something which reminds us commutative case and get integrability in some kind of way similar to what we have done in commutative case. And the result of his PhD thesis is yes, we can, and that's what I want to present. So namely, first let's discuss some coordinates. If P1, Pn are elements of Grassmannian, so we can try to lift the corresponding subspaces to choose some representative in space of 3k by k matrices. And if the lift is generic, then the column of freed such matrices make a basis in 3k. And then if it's a basis, then definitely we can express Vi plus 3 as some combination, some linear combination of three previous matrices Vi plus 1, Vi and Vi plus 2, where these coefficients are not scalar anymore, but some k by k matrices. So it's very similar to our commutative situation, but our coefficient, this coefficient is something like weights of the arrows and the diagrams that we discussed before. But our coefficients not commutative anymore. So they're k by k matrices. So it's why my official title of my talk was non-commutative integrability. Please don't, it's different non-commutative integrability that was described by David, completely different. Well, first simple lemma says that the lift can be chosen in such way that one coefficient can be make identity. So we choose this option, and for all i's we have such relation. So we have these coefficients xi and yi's. These coefficients are k by k matrices, and they exactly describe the corresponding. Those are parameters describing the space of Grassmann n-gons. This is a lemma. So xi and yi form coordinates on the phase space of Grassmann pentagram map just up to common JLK conjugation. This JLK conjugation disappears in commutative case because conjugation, you don't see conjugation. Conjugation acts trivially for one by one matrices. So again, simple computation shows that in those parameters, Grassmann pentagram map takes this following form: xi, yi goes into these expressions, and we can exactly try to do the following. So we take the previous pictures that we have drawn, the same oriented graph on the cylinder, put the same weights, but just think about the weights as some non-commutative variables. And then we can do some square moves and so on. Well, first of all, small, not very deep thinking shows that you can define square moves for non-commutative variables. You can also define these commutativity moves. So you can do the same sequence of moves as in commutative case, but just carefully treat your variables as non-commutative ones. And the result will be something which realizes non-commutative Grassmann pentagram map. However, the problem is with definition of Poisson bracket, because now you need to define Poisson bracket with the values for function with values in non-commutative field. There is a theorem that if you just take general associative algebra, non-commutative, and try to define Poisson structure, we satisfy all these axioms like Jacobi identity, Leibniz identity, and everything, that your Poisson bracket must be trivial. It is just commutator. So we don't want commutator. So we want something more general. So what is the way around it? And people thought about that. So the one way to think about that was suggested by Crowley-Bowie, which says the following. So for an associative algebra, take something which you call cyclic space. It is A sharp. It is just factor of A by commutator A with A. So, well, this space is not an algebra anymore. It is just linear space, vector space. And it's vector space generated by monomial expression in elements of AI up to shift translation. So if you have, yes. So ABC is the same as BCA. Well, it's obviously like that. So look that it's if you think about A, B, and C as a matrices, then it is this is a rule which is satisfied by traces of the matrix. Like if you take trace of ABC, it's the same as trace of BCA. So in that thing, elements of A sharp, it's useful to think about that as a trace of the corresponding K by K matrix. So definition by Crowley-Bowie says that H0 Poisson structure on A is a Lie bracket on this linear space A sharp, such that if you fix one element and consider it acting on the other elements, it's induced by derivation of A. Because we don't have multiplication, so we don't have Leibniz rule. This is sort of what should replace Leibniz rule. Theorem that, well, if we have this H0 Poisson structure, then it's induced kind of correct, it's kind of pushed down to the trace functions for any representation of A in matrices, and K by K matrices. Okay, now definition. By a non-commutative integrable system in A, we mean map T from A to A such that there is infinite family of invariants of our operation, so that Ti is kind of coincide with T of Ti modulo this conjugation. And also there exists T invariant H0 Poisson structure such that Ti sharp and Tj sharp Poisson commute for all ij. So now consider the expression for the Grassmann pentagram map in the xy matrices formally as a map on the free skew field in the indeterminants xi and yi. Theorem by Ovenhouse that Grassmann pentagram map is non-commutative integrable system in the free skew field. So you can find integrals, non-commutative integrals in involution, infinite family of such integrals, which really act for pentagram map. And moreover, well, I'm kind of going ahead of myself. So under representation, kind of if we kind of consider the representation of each parameter as K by K matrix and with trace function, then the collection of this invariant descends to invariance of discovered by Marie Beffe and Philippe. So in a sense, this is non-commutative avatar which can be projected to kind of Marie Beffe and Philippe results for all cases simultaneously. Okay, so how much time do I have? 10 minutes. To prove, well, now let's discuss probably some details of the proof. So proof is, to prove these results, it's convenient to use something which is called double bracket on associative algebra, because we want to use some sort of Leibniz identities. It's not very convenient when you kind of the space that you're working with is not an algebra. So to introduce Leibniz identities, you use something which was introduced by van der Berg, which is called double bracket on associative algebra, is bilinear map from A cross A to A tensor A, which you see satisfies some sort of Leibniz identity, for BC on the right, and also some sort of skew commutativity where, well, this thing, it just permutes X and Y in tensor product. Kind of some result of Van der Berg that double bracket induces bilinear skew-symmetric operation denoted by this angle bracket on a sharp given by the following. That first we take the double bracket of A sharp, B sharp is the following. We take two preimages of A sharp and B sharp, compute the corresponding double bracket of them, we will get element in A tensor A. Then consider the multiplication map from A tensor A to A. So when we apply this multiplication map, we will get some element in A. And now do sharp of this A. Kind of consider the projection to the cyclic space. This operation, so if you have double bracket, it induces some skew-symmetric operation in this cyclic space. This operation is not necessarily bracket, but when it is, we will have H0 Poisson structure. And now we kind of say that we discuss how we introduce this double bracket operation in our setting. So we have quiver, each H of the quiver is assigned some weight, non-commutative weight, x, y, z, or like that. And so we define double bracket, in this case we define double bracket of yz as y tensor z, and all other double brackets are 0, and in this case we define double bracket of bc like c tensor b, so kind of the order is exchanged to the opposite one, and all other double brackets is 0. Claim that it induced the correct angle bracket of F sharp. And this angle bracket is H0 Poisson structure. So this angle bracket now we can take as definition of the right kind of the Poisson bracket that with respect to what we would like to check commutation relations. So there is kind of non-commutative gauge equivalence, which is described by that thing, and so this is the quiver on the cylinder, which give us, which describe the phase space of non-commutative n-gons in Grassmann. So with each element xi, we can assign the loop in this space. And the loop has this following property that all arrows except 1 has weight 1. So the total weight of this loop is exactly xy, and this total weight of this loop is yy. And moreover, so if you just take kind of the standard Goldman bracket of these loops, well, the Goldman bracket coincides with our angle operations that we described here. Then we, well, this is, I'm just showing that we can define square moves by Postnikov in non-commutative settings by the corresponding formulas, which satisfy the same property that total weight of any passing through this, in this situation, coincides with the total weight. Well, our square moves do not change boundary matrices. And there is also kind of commutation relation, as I try to draw here. Well, so the pentagram map can be obtained by the sequence of this elementary move. And if we do the corresponding sequence, we will get the following non-commutative expressions, where these xi's, yi's should be understood now as non-commutative variables. Okay. So then we can do, in the same way as before, we can define the weight of the path But now we have to take the product of all weights of edges in the correct order. Because things non-commute anymore, we also modify it by the same spectral parameter in the same way as before. We define the corresponding boundary measurement. The matrix B of lambda change under pentagram map only up to conjugation. So we can conclude in the same way as before that trace of power of BI can be decomposed in the following way, and these Tij's are invariants, modulo the conjugation. So as elements in the corresponding cyclic space, they are invariants. And moreover, we can prove that they Poisson commute for all IJKL. So we will get sort of infinite collection of commuting elements in the corresponding cyclic space. Basically, this is almost the end, except that in commutative case, the proof produced by Ovenhouse is really combinatorial, and he really analyzed how paths intersect, more or less using some sort of association with Goldman bracket for these guys. And it was complicated, but in commutative case, we can, to prove that we discussed that we can use some R matrix formalism. Right? I don't want to keep you much longer, so what I just want to say is that there is R matrix formalism also here. We can develop some non-commutative R matrix here, which satisfies some R matrix property, and one can use that to prove this result. Okay. So, I don't want to well, you can write some Lax equation in non-commutative form. There is some theorem, but more or less I said everything. So I said that you can define this complete integrability in totally non-commutative situation. And that's end of story. Thank you. And as a last speaker, I would really very like to thank organizers for doing such a beautiful conference.
Questions?
What's so special about this galaxy cluster?
Because it's cluster.
Yes. So your coordinates PQ, if you apply like duality in a projective space or even in the Grassmannian, they seem to be interchanged. Does that duality is helpful at all?
Not on that one, but there is this duality. Yeah, there is duality, of course. Yeah, but kind of
doesn't quite help.
not really. Yeah. This duality is kind of more or less going from Grassmannian to the dual one.
More questions?
You have one quiver that's you have a path and quiver, right? And if the path is closed, is a map in the torus?
Yes. Yeah. It's related to, well, there is generalization of this construction described by Goncharov and Kenyan when they consider this like black, whites, and torus, and it's connected to dimer models on the corresponding graphs. So basically, well, this spectral curve, which is in our case is obtained as determinant of this boundary measurement matrix, can be obtained as a partition function of dimer model when you consider this, well, the corresponding black-white graphs on the torus.
Right. Thanks.
Okay, so let's thank the speaker.
Are there plans? No, right?
Oh, we're free!
So stay. Last words, right? Well, first of all, for a change, the organizers were spectacular, right? And then we recall their names, right? Ricardo, which is already working like a done somewhere else. Oh, there he is, right? Juliana, Nicolau, Paulo, Abilton, wonderful. The guys from the secretary and both here, right, as usual, they did a fantastic job. But you know what? We should thank also the guys at the conference, right? I was extremely grateful that you guys came. You showed wonderful things, right? We shared yet another time. This amazing fact that mathematics is spectacular, right? And let's just find more and more excuses to meet and to share the wonderful things we have around us, right? I thank you with all my heart. Ciao!